In our previous lessons, we've been looking at different patterns that generate sequences of numbers. And from these sequences of numbers, we've been trying to write recursive routines to represent them, and then use those recursive routines to do some estimations for what certain terms would be based on the givens. And the key when we're looking at these sequences of numbers is, first of all, one, not only how are we going from one term of the sequence to the next, whether we're adding, subtracting, or multiplying by a value, but also what are we starting with? Are we starting with a beginning amount, which would be like your term 0, or are we starting with just the first term or stage 1 of the sequence of numbers? So it's important that you distinguish between the two, because if you don't write your recursive routines with your term 0, your beginning amount, if it was, let's say, a word problem as well, that will impact what you're writing down as your terms for your values. So as we look at these numbers here, we can see we've got 8, 24, 72, 216. And the differences between those numbers are too large to be a common difference where we're adding or subtracting a common amount. So if you're looking for a multiplier, remember you're taking the current term divided by the previous. So I'd be looking at, well, what's 24 divided by 8? 72 divided by 24, 216 divided by 72. And that would tell me what the common multiplier or that common ratio would be to use for this sequence. And so we can see that it's a multiple of 3 from one term to the next. And since this is the 0 term, the beginning part of our sequence, I'm going to use that to start my recursive routine. So I'd have 8, enter, answer, times 3, enter, enter, enter to find the next term of my sequence. So because I have this common multiplier, we talked about before the two different types of sequences we can have. This is an geometric sequence. An arithmetic sequence, again, is when we're adding or subtracting a common amount. Now, since we have the geometric recursive routine, we could take that and turn it into an equation, which might be easier for us to find a certain number term in the future. Or if I want to work on finding the term right away, I can just start with this. And remember, after I enter that first time after this rule, that would give me the second term for 24. Next time would be the 72. Next time would do 216. I would have to count and make sure I'm doing it 15 times to get that term. So you might find the equation a little bit easier to help you do that. And so remember, the equation means you're starting with an 8 and you are multiplying by 3 each time. So that would look like an exponential equation. So I've got 8 times 3 to the power of n. Now, if you were typing that into your calculator or class kick, remember you're going to have to use the caret key to show that you're using it as an exponent, repeated multiplication. So if I want to find the 15th term, I can take 15 and put it in for n and see what results. If I'm taking 8 times 3 15 times, I end up with our number here. 114,791,256. And again, you don't have to put the commas in if you were typing things like this into class kick, or if you like to help you think about the value, that is up to you. And so this is overall what we've been doing the last 4 or 5 days with our various situations that we've seen in class that you got on your 1.1 worksheet. And so we're going to continue building on those items today. So here's our next sequence of numbers. -18, 6, -2, and 0.6 repeating. Notice this time they said -18 is your first term. So that's like stage 1 when we were doing our experiments when we started the unit. So could we write a recursive routine to represent this? Sure. We are starting with the first term of -18, and notice how it's going from negative to positive to negative to positive again. That's only going to happen when you have a common multiplier, common ratio, because a positive times a negative would be a negative, right? That will not happen if you have a common difference of addition or subtraction. So in order to find out what that common ratio is, just like we did on the previous one, if I take the current and divide it by the previous, current divided by the previous, and so on, I should see what that ratio is. And so you could use the calculator to help you, or if you're doing it in your head, we should know that the ratio would be a negative 1/3. Now, the only thing is we don't have our beginning value, right? We need to have our a sub 0, the initial value. We have the first term. So if I'm thinking about going forward in my sequence, I'm always multiplying by 1/3, right? So to go backwards in the sequence, I would have to undo that, right? So if you're multiplying by 1/3, you could divide by 1/3, or you could think of it as multiplying by a -3, the reciprocal of your multiplier, and that will tell you what you're starting with for your sequence. So if we do that, we would have a 54 as our initial term, our 0 term. So we'd have our recursive routine of 54, enter, answer times negative 1/3, enter, enter, enter. And again, it's geometric because we have that common ratio, that common multiplier. So if I want to talk about writing the equation, I have all the pieces that I need to write my geometric representation, which would be 54 times a repeated multiplication of 1/3 again and again and again. So if I wanted to find my 15th term, I could put 15 in for my exponent and do my calculation to get that. Or if you wanted to continue with the recursive routine, remember each time that you would enter after the 1/3 multiplier, they would count, right? And that would get you to the same result. So we end up with negative 3.7633528 times 10 to the negative 6, or you have its decimal representation here. So it's a number really, really close to 0. All right, if we look at our third one, here's our sequence, 17, 10, 3, and -4. And notice how they're saying that 17 is the first term in your sequence. So let's have you pause the video here and see if you can write the recursive routine, what type it is, an equation, and what the 15th term would be. So as I look at the sequence of numbers, I see a pattern emerging, 17, 10, 3, -4. I know I have a common difference of 7 each time. Now, the only thing is when I go to write the recursive routine, I have to have my initial term, and 17 is not it. That's my term 1. So since in my sequence to go forward, I'm subtracting 7, to go backwards, I would have to undo that and add 7. So 17 plus 7 would mean 24 would be my initial term. Because I have a common difference, I know it's an arithmetic sequence. And I can take that recursive routine and turn it into my equation pretty easily by knowing I have to start with 24 and I'm taking away 7 each time. So I could write that as 24 minus 7n. To find the 15th term, again, you could go to the recursive routine and just count 15 enters of taking away 7. Or I could put 15 into my equation for n and find my term value that way, and that would result with a -81. So again, this is just formalizing everything that we've been doing the last 4 to 5 days, trying to take your different situations, the recursive routine, the pattern to see if they're going to be arithmetic or geometric, and then using that to do some estimations for various terms along the way, or write some more explicit equations to go with them. So continuing with this idea of our values here, remember we're talking about a sequence. It's an ordered list of numbers, and each number we would call a term, and it's usually denoted by a variable with a subscript. Usually they talk about A representing the term, and the subscript is going to give the terms a place in the list. So for example, with my sequence of 13, 19, 25, 31, and so on, 13 is the first term in the sequence, 19 is the second term, 31 is the fourth term. N just means for any term in my sequence, right? What could I do to determine that? So we would say A sub n is representing that term in the sequence. We've always been able to try to write rules to represent how we're finding those terms in the sequence, and those were your recursive definitions, your recursive routine. So if we want to take that sequence, we could always arrange in a table if that helps. And we've done that before with our first experiments. If you think back to your Sierpinski's triangle or the block layouts that we were doing in the L shape, we had something that looked like this, right? And so we've got our terms and we have the values in the sequence. How can we use that to write that recursive definition to make those predictions? Just like we were doing in the warm-up, just a little bit more formalized here. Well, just like we were doing before, we said they're always defined starting with your initial term or zero term. So if we're not given that initial term, whether it's a word problem or just a sequence of lists, we have to calculate what that would be. So in order to do that, we've got to find what the difference or the ratio is in our sequence to make that happen. So I'm looking at my terms 13, 19, 25, 31. I see that there is a common difference between each of those values, and they're increasing by 6 each time. So if I know I have a repeated addition of 6, I can use that to find the initial term, and that would then give me all the pieces I need to be able to generate any term in my sequence list, as long as I know what term value that's going to be. So if I was adding 6 to go forward, to go backwards, I would subtract 6. So what plus 6 gave me 13? Well, that had to be a 7. So now if I'm putting those items together, I can figure out for any term number I'm asked to locate what to do. Because I have the initial term, I have the common difference, I can put those together to write my equation. And that would be, equation would be the initial term plus the common difference over and over and over again. So 7 plus 6n. So if we think about the development of how we came up with this recursive definition, right? Everything was based on the initial term plus that repeated addition of the common difference. So if we're talking about that initial term, a sub 0, I know what the difference is and how many times I need to put that to my initial term, I should be able to come up with my explicit formula for that sequence. Now, because it was a common difference that we were talking about it, this is for an arithmetic sequence. So here's our pieces. For any arithmetic sequence, you always have the result based on the initial term plus the term number times the common difference. Why is it important? Because if I know what term I want to calculate, I can just substitute that term number into my formula and calculate its value. Or if I have a value in the sequence, I can determine what term that's representing. So let's continue to build off what we were just using with that sequence and do some predictions. So here's our sequence. We came up with our pattern for our formula, 7 plus 6n. And now I have something like a sub whatever is equal to 67. So we're saying, hey, what term has a value of 67? Knowing the formula, I could undo it to find the term value. So 67 is my result, a sub n. So if I replace that into my formula, I just have to undo my order of operations to solve for n. So I see I have a positive 7. I would subtract 7 from each side. Then I see I have a multiplication of 6, so I would divide 6 by each side. It's telling me, hey, the term of the sequence that gives me a value of 67 is 10. This is the 10th term in the sequence. Now, If we had something that looks like this, a sub 15 equals, that's asking you, can you find the value of the 15th term in the sequence? And this is similar to kind of what we're doing for the warm-up, right? I know the term number, n. I can substitute it into my formula and do the calculation to find its value. That's saving me from hitting enter that many times to find it in my sequence, right? So all I have to do is 6 times 15, add my 7 to that, and I'll have 97. So the 15th term in my sequence is 97. So you have a couple of more sequences given to you, and you're going to do the same process as what we've been doing for the warm-up and their last example. Based on the pattern that you see, you are going to find the recursive routine, right? So think about that. How are you going from one term to the next in the sequence? And if you're not beginning with the initial value a sub 0, you have to calculate that first so you can use it to get your explicit formula. Okay, that goes for arithmetic, geometric. It's been the same thing that we've been doing up to this point. Once you have your pattern, then you can do your prediction. So if I give you a value in the sequence, can you tell me what term it's representing? And vice versa. If I tell you the term in the sequence, can you calculate its value? You're going to put your answers on your paper if you want to start, but check them in class kick. You should get green outlines if you're on target. If not, you'll get a red for try again. Use the raised hand feature so I can assist you to make sure you're on target with your objectives and give you hints as to where your misconceptions are. Please, please, please show your evidence. So whether you're doing it on paper or typing everything into class kick, show me what you're thinking to come up with the results so I can pinpoint where the errors are. And then we'll be able to do more practice tomorrow.